Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we are at lecture 21 and this is week 11. Today's topic is op-amp comparators. That is, we are now moving to a new topic of op-amp comparators. Previously we were taking op-amp as an amplifier and use negative feedback to reduce the gain to a lower value so that we can use it as an amplifier, and the output of the op-amp do not go into saturation. But now from onwards we are now moving towards the comparators in which you use either no feedback or positive feedback. The impact of having no feedback and positive feedback would be that the gain of the amplifier would be very large and is called the open loop gain of the amplifier. So if the op-amp is not having any feedback, that is, it is operated in open loop, then the gain of the amplifier would be very high, and the effect of having the large gain would be that op-amp would always be in saturation. That is, the output of the op-amp would be saturated to its one-off supply level, that is plus VCC or minus VCC. Even if op-amp has a positive feedback applied, then its gain would be even higher than the open loop gain. So in case of positive feedback, because of the gain even higher than the open loop gain, the output would remain into saturation, and op-amp output would be saturated at its one-off supply levels, plus VCC or minus VCC. So we are now taking the op-amp in considering the op-amp in positive feedback or without any feedback, and see how this op-amp can be used in different applications if we are not applying any feedback. And we will see that still op-amp can be used in a lot of applications in comparator mode, where it can be used as a comparator in lot of applications that we will see later on. These are the lecture contents. Op-amp comparator operation. We will see application of op-amp as a level comparator, zero crossing detector. Then we will move on to positive feedback in op-amps, and the application of positive feedback is Schmidt trigger. We will see inverting Schmidt trigger and non-inverting Schmidt trigger. So what is a comparator? A comparator, as its name implies, compares the voltage levels which are applied at the input of the op-amp. So the input that you are applying at the op-amp is a voltage. So the comparator what comparator do is it compares those input voltages applied to either input of the op-amp and produces an output depending upon the comparison of the inputs applied. Now since the op-amp has two inputs, the voltage level of one input is compared with the other. Based on this comparison, the op-amp produces an output to indicate that voltage at one terminal is greater than or less than the second terminal. So what it do is it takes two inputs, and based on the levels of the inputs, uh, which voltage is higher than the other. Depending upon that, it produces an output to indicate that level comparison of the input terminals. So the op-amp usually takes an input signal which is a linear voltage. The input may be a DC constant or changes linearly, and produces a digital output that would be either at high level or at low level, that is at plus VCC or minus VCC, because I told you that output only can have two possible levels, plus VCC or minus VCC, because the op-amp is always in saturation mode. So output can be of any value, any level, but output would always be at one of its two possible levels. So the output will be high when the voltage at non-inverting input is higher than the inverting input, and vice versa. That is when voltage at non-inverting terminal is higher than the inverting input, the output would be high, and if voltage at inverting input is higher than the voltage at non-inverting input, the output would be low. This is the symbol of the operational amplifier with these two inputs. This is non-inverting terminal, this is inverting terminal. These are the supply levels plus 12 volts. This is either 0 volts or minus 12 volts or some negative supply voltage. Here it is applied 0 volts. This one is the output. So these are the inputs for voltage comparison. So you can apply input on either terminal or both terminals. So if voltage is higher on this pin, that is on non-inverting pin, the output becomes plus 12 volts, and if the voltage of this terminal is higher than the non-inverting terminal, then the output would be at 0 volts. So this is a basic unit, and this is typical application in which you have applied inputs to each terminal. However, at inverting terminal you applied plus 2 volts DC, which is also called reference voltage, and on the second terminal you applied an input signal that can be any waveform, sinusoidal, triangular, or any arbitrary shape, and based on the level of these inputs, the output would be defined. Whenever the input is input levels are such that VD is greater than 0, that is VD is defined as voltage at positive terminal minus voltage at negative terminal, and if voltage at positive terminal is higher than this terminal, then VD would be positive. So output would go to 2 plus VCC or 10 volts, and if VD is less than 0, the output would be at minus VCC or minus 10 volts. First we consider the non-inverting comparator, and we want to see what would be the output of this comparator for input of, let's say, a sine wave applied with a peak value of Vp, and this Vp is higher than the Vref of plus 2 volts. So might be it is 5 volts, let's say, and Vref is 2 volts. So input is a sine wave and Vref voltage is 2 volts. Then what would be the output that we are going to see? So First of all, we start with the assumption. Let me start with the point where input is at 0 volts and voltage at the positive terminal is plus 2 volts. Input is 0 volts and voltage at negative terminal is plus 2 volts. So it means that you would have 0 volts at this point. Here the voltage would be 0 and voltage at this point would be plus 2. Then what would be VD equal to VD would be equal to V plus minus V minus, that is voltage at positive terminal or non-inverting terminal minus voltage at inverting terminal, and voltage at positive terminal is 0 volts and voltage at negative terminal is plus 2 volts. So result would be minus 2 volts, so which is less than 0 volts. So whenever the voltage VD is less than 0 volts, output would go into negative saturation. So output would be at minus Vsat at this point when Vin is 0 volts. Now if Vin is increased to, let's say, 1 volts, then what would be the output at this instant? That is, now input is increased to 1 volts, then then voltage at V plus is 1 volts and voltage at V minus is still 2 volts because this is constant reference voltage, DC voltage. So answer would be 1 minus 2, which is minus 1, and still it is less than 0. So as VD is less than 0, so output would still be negative minus Vsat. So output would stay at a negative level. When this output would go to positive level, that we are now looking at, as Vin is increased and reaches at this point, which is a level of 2 volts, and then crosses this level and attains a value higher than 2 volts. For example, it is at 2.1 volts. So when input is increased and reaches at 2.1 volts, then voltage at this point will become 2.1 volts and voltage at this point is 2 volts. Then what would be VD equal to? VD equal to 2.1 minus 2. What would be the answer? Result would be plus 0.1. Plus 0.1 is VD, which is greater than 0. Now whenever VD is greater than 0, output would go into plus Vsat or plus Vcc. So at this instant, when input crosses this reference level, output would switch to the positive level and becomes plus Vsat or plus 10 volts. Now when input is further increased, then this voltage would be higher than this voltage, then output would stay on high level of plus 10 volts. This is plus 10 volts. And when input goes back and decreases and crosses this point again and becomes less than this level, then the voltage at this terminal would be lower than this terminal, and then VD becomes negative. Whenever the voltage of this terminal is lower than this terminal, then VD becomes negative and output would go into a negative saturation of minus 10 volts. So voltage here at this instant would be minus 10 volts. Again, when input stays below this level, the output would remain at minus 10 volts up till this point where input crosses this level and the voltage of positive terminal is increased from the negative terminal. Then as a result, output would again switch to the positive saturation level. So you can see that the output would stay at high level whenever input is greater than V reference, and it would stay at low level whenever the input is less than V reference. So this is the comparator which compares the voltage of this terminal with the other terminal, and whenever the voltage of this terminal is higher, the output goes to high logic level, and whenever the input is below this level, the output goes to negative. So this voltage of this terminal is compared with the voltage of this terminal, and based on this comparison you get the output of the op-amp, and indicates you the and give you an indicator of the signal. That signal has crossed this level and becomes higher at this point and during this situation, this interval, and it crosses this level again and becomes lower than this level during this interval. Next is inverting comparator, in which input is applied at the inverting terminal, and here we are again applying a sinusoidal input, and this sinusoidal signal is compared with the reference level of plus 2 volts that is indicated here. Now again we start the analysis of the circuit by considering the input level starting from 0, that is at this point. So when input is 0 volts here, then voltage at non-inverted terminal is plus 2 volts. So VD would be equal to what? VD is always V plus minus V minus. So V plus is 2 volts and V minus is 0 volts. Then answer would be plus 2. So as it is greater than 0, so V out would be plus VCC. So at this instant output would be at plus VCC. Then if input is increased and it crosses this level and becomes equal to 2.1 volts, let's say, then voltage at this point would become 2.1 volts, and VD becomes 2 minus 2.1. So answer would be minus 0.1, and minus 0.1 is less than 0. So output would go into negative saturation. So after this level, if input is increased from this level, then output would go into negative saturation. Again, when input is decreased and becomes lower than this level, then what happens? The potential of this terminal would be higher than this terminal, and the output would be at plus VCC. So this is the output during this interval. And from this point to this point, again voltage of the negative terminal or inverting terminal is higher than the non-inverting terminal, so output goes to negative saturation level, and so on. So this is how comparator works, that it compares the input signal levels, and based on the comparison it provides an output which would be either at high state or at low state, depending upon the difference of these two voltage levels. So as you see that when Vd is greater than 0, output would be plus Vcc, and when Vd is less than 0, output would go to minus Vcc. In this slide we will see how the reference level can be set on any terminal of the op-amp. That is, how can we set a reference level of, let's say, plus 2 volts at inverting terminal here, or at non-inverting terminal in this case. So we can use a DC supply or DC voltage source, and through our resistive voltage divider we can set the value of this node to any desired value by choosing the appropriate values of resistors and this power supply value. So for let's say 2 volts here, I can take a 6 volt power supply, 4 volt power supply, and take these 2 resistors are of equal value. Then I can set, I will get a 2 volts DC at this node. It sets the reference level, and the voltage at the terminals is a input signal coming from your desired application to which you want to compare and produce the output. This is a zero crossing detector, which is a special case of a reference level comparator, in which now reference level is 0 volts. So it is a zero crossing detector. That is, this circuit detects the signal whenever the signal crosses 0 volts. That is, it gives an indicator at the output of the op-amp that the signal has crossed this 0. Either it goes from negative to positive, or from positive to negative. The output would be changed from one logic level to the other logic level. So that is, in this case, whenever the signal goes from negative to positive and stays positive in this region, the output would be high, and whenever the signal crosses 0 and stays negative, the output would go stay at negative saturation or at low level, and again when it crosses the 0 and becomes positive, the output go high again. So this circuit simply detects the 0 crossing of the signal applied at the input. Next is positive feedback in op-amps. When output of an op-amp is fed back at the non-inverting terminal, that is the positive terminal, then it becomes positive feedback. So positive feedback means you apply a connection from output and connect it to the positive terminal of the op-amp, then the op-amp becomes then the circuit would be in positive feedback. The result of the positive feedback is that the gain of the amplifier or op-amp gets increased from its open loop value. So the result of positive feedback on gain would be, the gain would be very high, and it would even be higher than the open loop gain. of the op-amp. So as a result, the output of the op-amp will always be saturated to its one of the supply levels. So whether the op-amp is in open loop or in positive feedback, in both cases the gain would be very high and op-amp output of the op-amp would always be saturated. Why we are using positive feedback? There are applications of the op-amp in which op-amp is used in positive feedback. One of the application is Schmidt trigger. We will see later on some other applications of op-amp positive feedback, that op-amp is used in oscillators where you use positive feedback to produce certain oscillations using op-amps. So in this section we are going to introduce Schmidt trigger. What is a Schmidt trigger? Schmidt trigger is basically op-amp with positive feedback, and the purpose of the Schmidt trigger is to convert any regular or irregular shaped input waveform into a square wave voltage or pulse. So first of all, the job of the Schmidt trigger is to convert input shape which is of any irregular or regular form. It always produces an output which would be a square wave. That is, it can also be called as squaring circuit. So Schmidt trigger is a squaring circuit which takes input of any shape but produces a output, square wave output. The second function of the Schmidt trigger is, the Schmidt trigger is a logic input. It is a logic input type that provides hysteresis or two different threshold voltage levels for rising and falling edge. This is useful because it can avoid the errors when we have noisy input signal from which we want to get square wave signal. So Schmidt trigger has the ability to avoid the error that could possibly be produced in the output because of the noise in the input signal, that we will explain it later. The advantage of positive feedback is that the resulting comparator Schmidt trigger circuit is immune to erratic triggering caused by noise or slowly changing input signal within the hysteresis band, producing a clear output signal, as the op-amp comparator output is only triggered once at one trigger level. So this is an inverting Schmidt trigger. Similarly, we would have a non-inverting Schmidt trigger. The inverting Schmidt trigger is the one in which input is applied at the inverting terminal and have a feedback that is positive. So for a Schmidt trigger there would always be a positive feedback, and for an inverting Schmidt trigger this feedback is on positive terminal and input is at inverting terminal of the op-amp. So this circuit is called the inverting Schmidt trigger. So how this circuit would operate, that now we are going to see. So first of all, to analyze the circuit, we start with the assumption that because of the fact that op-amp is connected in positive feedback and the gain of this amplifier would be very high, so that for any input the output would always be in saturation, that is one of its supply level, either plus VCC or minus VCC. So output would always be either plus VCC or at minus VCC. So to start with, we assume that the output is one of its supply level. सो चूँकि आउटपुट जो है वो इन दो लेवल्स में से किसी एक लेवल पे ही पॉसिबल है, तो हम एज्यूम कर लेते हैं कि आउटपुट हमारे किसी एक लेवल पे है, और लेट से हम एज्यूम करते हैं कि आउटपुट प्लस वीसीसी। तो अब अगर मेरे पास आउटपुट जो है वो प्लस वीसीसी पे होगी, तो इस केस में मेरे जो इस पॉइंट का पोटेंशियल होगा वी एफ, उसको मैं किस से कंप्यूट कर सकता हूँ। यहाँ पे इन दो रजिस्टर्स को अगर मैं देखूँ तो इसमें से जब यहाँ वोल्टेज यहाँ पे कोई प्लस वीसीसी अप्लाइड है, तो जो इसमें से करंट फ्लो करेगा, that current would flow in this resistance, and this same current would flow in R1 as well, because there would not be any current into the input terminal of the open because of the high input impedance. So this current would be equal to this. So these two resistors are in series. Then so we can apply voltage divider formula to find out voltage across of R1, which is also equal to VF. So VF is equal to R1 into VCC divided by R1 plus R2. So this would be some positive voltage because resistors have no sign or no polarity. So VCC, I am assuming that it is plus VCC. So this VF would have some positive value. And the input is a time varying signal. So when input is lower than this level, the output would be plus VCC, and as Vin increased and goes above this set level or reference level, then Vd becomes negative and output goes into negative saturation and becomes minus VCC. So as you can see that, for example, if I am assuming that Vout is plus VCC, then if input is increased and crosses the this level which we have defined here as VF, and this VF is called the upper trigger point or UTP, which we have indicated in the slide as VUTP or VUT, upper trigger. So this is the constant level which would appear at this terminal whenever the output is at plus VCC. So up till this point, output would be at plus VCC, and as if Vin increased and crosses this level, then what happens is the voltage at this terminal becomes higher than this terminal. Then output would go into negative saturation. So at this instant, the output becomes negative, and as the input goes negative, it is minus VCC. Here it is minus VCC. Then what would be the value of VF? VF would become equal to minus R1 into VCC divided by R1 plus R2, because at this point voltage is negative, so this voltage would also become negative. So with this negative is VF, which is also called lower trigger point, and this level would be compared with this, and the output would be computed. That you can see that now if input is again reduced and crosses this level, which was UTP, which was some higher level, but at this point as the input crosses this level, output would not change. Keep in mind that when input was increased and crosses this level, output was toggled, but when the input again reduced and crosses this level, then output would not be toggled. As you can see that because of the fact that now this voltage becomes negative, and only when this terminal voltage is reduced and becomes lower than this negative level, then VD becomes positive and output goes to plus VCC. Now as you can see that the input was the output was toggled to minus V set when input crosses this upper trigger level, but again when input is reduced and crosses this level, the output would not change from negative to positive saturation level until it crosses the second trigger point, that is LTP, which is defined by this equation. It is called lower trigger point because when this voltage becomes negative, then the output would only be negative when the voltage at this terminal becomes more negative than this level, so that this voltage becomes more positive than this, then output would go to plus saturation level. Similarly, when input goes to plus saturation level, this becomes plus VF that we have defined using this relationship. Whenever Vout is plus VCC, then voltage at this point VF would be plus some positive value, and when this is some positive value, then if the output is plus VCC, then it would go to minus VCC only when the voltage of the negative terminal is becomes lower than this level, is higher than this level. That is, at this point the input becomes higher than this level, then output goes to again negative saturation. Next we would like to see the hysteresis curve and hysteresis band. What is the hysteresis curve? The hysteresis curve is the relationship between input and the output of the op-amp. The input is the input signal that is applied, and the output is defined here. This is the output. Now you can see that the output only has two possible levels, plus V set and minus V set. These are the two only possible levels. However, input can have any value. It can be 0, it can be positive, it can be negative, and input is changing, but output stays at one of its two levels, either plus V set or minus V set. So here we define trigger points VUT and VLT with respect to the input. That is, when input is increased and crosses this trigger point, then output would be changed from one level to the other level. Similarly, when input is decreased and becomes negative and it becomes lower than this trigger point, that is LTP, then again output would be toggled from one level to the other level. So output can only toggle from one level to the other level at these trigger points, which are defined as VUT and VLT. So for the inverting comparator or inverting Schmidt trigger, the statistics would be such that whenever the input is increased and crosses the upper trigger point, the output becomes negative. It changes states from high level to low level. As you can see that the input when is increased and crosses the upper trigger point, it changes from high level to low level. And for the lower trigger point, when input is decreased and crosses the lower trigger point, and then output becomes positive. That is, shifts from negative level to positive level. That is, you can see that when output was at negative level, it would shift to the positive level. When input crosses this trigger point, the output goes to the positive level. Again, when output goes to positive level, it would return to the negative level only when the input is crosses the upper trigger point. So when input crosses the upper trigger point, output becomes negative, and when input crosses the lower trigger point, the output becomes positive. So you can see that when input is increased and crosses this trigger point, output becomes negative, and when this output becomes positive, when input is decreased and crosses the lower trigger point. At this point, output would become high. So this is how the negative Schmidt trigger works, and this is how the positive feedback works. That positive feedback introduces a hysteresis into the circuit, and because of this hysteresis, only the output would be affected when you crosses this hysteresis curve on either side, and within the band, which is called the dead band, output would stay on its previous value, whatever the value is, and only changes the state when you cross this dead band on either side. That is when input is 0, the whatever the output is, for example output is plus VCC, then it would go to minus VCC when you cross this trigger point, and then goes negative, and this stays at negative all the way from the dead band. This when this dead band is crossed, and you crosses the lower trigger point, then only the output changes the state. So this is called the hysteresis band or dead band, and it is defined as, this is the width of the hysteresis band, and it is defined as VUTP minus VLTP. Now let's see an example for the circuit in which you have input applied at the inverting and have a value of 5 volts peak, and it is a sinusoidal. These two resistors are given. This is 1 kilo ohm, this is 5 kilo ohm, and the supply levels are plus 12 and minus 12. Then you are asked to find out the upper trigger point and lower trigger point. Then in part B, you have to calculate the hysteresis band, width of the hysteresis, and in part C, you have to draw the hysteresis curve like this, and then in part D, you have to draw the output waveform of this for the circuit for the given component values and the input signal. So first of all, to solve part A, you have this defining equation for UTP that is defined with these components and the supply level. With R1 is 1 kilo ohm, supply voltage is 12 volts, and R2 is 5 kilo ohm. 5 plus 1 is 6. 12 by 6 is 2 into 1, 2 volts. So UTP is 2 volts, and similarly LTP is a negative level, which is defined by this relationship, and this becomes minus 2 volts. Then you can calculate the hysteresis band, that is defined as VUTP minus VLTP. That would be equal to 2 minus 2, so it would be 4 volts. So hysteresis band would be 4 volts. Then in part C, you have to draw the hysteresis curve. The hysteresis curve is the relationship between V in and V out, and on the x-axis you define trigger points. That is, one is plus 2 volts, the other one is minus 2 volts. This is origin, and at these trigger points the output would toggle from one level to the other level. As you can see that this is an inverting comparator, so if the output is at high level, then it would go at low level when you cross the upper trigger point, and it would change from low level to high level when it crosses lower trigger point. And then you can draw the output waveform using the behavior of using these trigger points and the behavior of the circuit. As when input is crossing the upper trigger point, the output would become low, and it would become high when it crosses the lower trigger point. Next is the non-inverting Schmitt trigger. Non-inverting Schmitt trigger is the circuit with op-amp having a positive feedback, and input is applied at the non-inverting side. So feedback is positive and input is also applied to the non-inverting terminal. Then the circuit becomes non-inverting Schmitt trigger. So again, in order to see the behavior of the circuit, we will proceed in a similar fashion as we done with the inverting comparator. So again, we assume that output is one of its possible levels, that is at plus VCC. Then with plus VCC here, we define these two currents, which would be equal, and then writing the equation for these two currents, that is I1 would be equal to VF minus Bin divided by R1, I2 would be equal to V0 minus VF divided by R2, and then manipulating this equation and solving this for VF, we end up with this relationship with VF as a function of V0 and Vin. Now this is an important point, that is, in this equation the output we have defined is plus VCC. Output we are defining as plus VCC. We are assuming that output is at plus VCC. Then this VF is equal to V positive. This is the positive terminal at which feedback is applied, and this load is being defined as VF, which is also equal to voltage at the positive terminal, non-inverting terminal of the op-amp. So with this V0 as VCC and VF as plus V plus, this equation is written as V plus is equal to this one. So output this is very important observation, that the output will remain at high state as long as the input remain positive. That is, you can see that whenever the voltage at the plus terminal is some positive value, that is, you can see in the circuit, whenever the voltage at this terminal is some positive value, then it would always be greater than, this means it is always greater than 0, then output would always stay at plus VCC. Read this statement again, that output will remain at high state, that is at plus VCC, as long as the input remain positive. So from this equation, if input a signal which is applied is a positive number, as long as it is positive number, all the other factors are positive, this VCC is positive, resistors are of dimensional of absolute values, they have no polarity, so this V plus would always be a positive value. So if you plug the value of V in of any value which is always positive, then this would always be a positive number. So as long as this V plus is positive, output will remain positive. Now with the Vd equal to V plus minus V minus, so for output to switch from plus VCC to minus VCC, the value of V plus should be such that Vd becomes negative. So V plus should be such that Vd become negative. So when Vd become negative, from this equation you can see that as V negative is 0, so Vd would be equal to V positive. So this means that Vd would become negative only if V plus becomes negative. So in order to Vd become negative, V plus should be negative, so that Vd becomes less than 0 and output switch to minus VCC. So that for that to happen, input should become negative, as you can see in this equation, that for V plus to be negative, this input signal should be some negative value. So the trigger point would be the instant of the input signal when its value is when the input signal value is such that V plus becomes equal to 0. What that means is that for input signal of some negative value where this V plus becomes equal to 0, then Vd becomes equal to 0, and after that instant of the input signal, if input signal is further goes lower than this level, then Vd becomes negative. So first V plus becomes 0 and at this input level, and then you further reduce the input signal and V plus is decreased from 0, then only Vd becomes negative and output would switch to minus VCC. So the instant at which V plus becomes equal to 0 can be computed from this relationship by setting the value of V plus equal to 0 in the equation 1. So from which we can compute the value of input that would be equal to minus R2 into VCC divided by R1. So simplify this equation, you will end up with this relationship, and this level of the input which is some negative value at which V plus becomes equal to 0, and it would guard the lower trigger point, after which if input is further decreased from this level, the output would be such that output would be changed from high level to the low level. In a similar procedure, this similar procedure can be followed to find the value of upper trigger point. This would be the relationship for upper trigger point that you can develop by following the same procedure. I would recommend that you try it by yourself to come up with this relationship for upper trigger point. So for a non-inverting comparator, as the input increases and goes above UTP, this is UTP, upper trigger point, then voltage VD becomes positive and output will trigger to plus VCC. So as this trigger point is crossed, then output becomes plus VCC, and it stays at plus VCC until input crosses the lower trigger point. So at this point the output would be changed and becomes negative, and the output would again change from negative to positive at upper trigger point. This is the hysteresis curve, and this is the hysteresis band or dead band. For the non-inverting comparator, as we have discussed, the output would go from negative saturation to positive saturation when upper trigger point is arrived, and it stay at positive saturation until a negative or lower trigger point is arrived. At that point the output would become negative and stay at negative until the upper trigger point is arrived. Next, this is the example for non-inverting Schmidt trigger, that in this case the circuit is given with these values. R1 is 4K and R2 is 1K. With VCC is plus 12 and minus 12 volts. Input is applied at non-inverting side with value of 5 volts peak and of sinusoidal in nature. So again you are asked to find out UTP and LTP, then hysteresis, and you have to draw the hysteresis and draw the output corresponding to the given input. So this is the output you have to find out for this input. So these are the formulas that you can use to find out the trigger points. So by plugging the values of R2 and VCC 12 volts, R1 4K, so 1K into 12 divided by 4K, it becomes 3 volts. Similarly for LTP, this same formula with negative sign, so it becomes minus 3 volts. And hysteresis band, that is defined as UTP minus LTP, 3 minus 3, which is 6 volts. Then you can draw this hysteresis curve as we have seen for the inverting circuit. The only difference is that output is toggling from the negative level to the positive level when upper trigger point is arrived. and from positive to negative it will go at LTP, and you can draw the output corresponding to the input in a similar way. So that's it for today, students. Take care. Allah Hafiz.